Somewhere above your roof tonight, a star is collapsing in less time than it takes you to blink, while another star, smaller and dimmer, is dying so slowly that it will still be dying long after the last galaxies have gone dark. Both of those things are happening right now, and both are completely ordinary. Over the next couple of hours, we are going to walk very gently through every way a star can end, from the quiet ones that simply fade to the strangest deaths of all, the ones that leave nothing behind. Before we begin, leave a comment and tell me which part of the world you are listening from, and what the clock says where you are. I find it calming to picture all these different rooms, scattered across continents, lit by the same old starlight. Now let your shoulders drop, and we will begin slowly. Let me take a breath here, and let you take one too. There is no hurry tonight. Nothing in this story needs to be finished, or solved, or understood all at once. Stars take millions and billions and even trillions of years to do what they do, and we have borrowed only a small, warm corner of one evening to think about them. So if your eyes grow heavy partway through, that is perfectly fine. The words will keep going on their own, the way the light from a distant star keeps traveling long after the star itself has changed. You do not have to follow every detail. You only have to rest and let the ideas drift past like clouds you do not need to name. We are going to talk about death tonight, but not in a way that should trouble you. Because when a star dies, it is not really an ending the way we usually mean the word. A star dying is a slow handing over. It is matter passing from one form to another, light becoming heat, heat becoming pressure, pressure becoming new elements becoming, eventually, the ground under your feet and the iron in your blood. Stars die the way a fire settles into embers, and the embers warm the room long after the flames are gone. That is the kind of death we will be sitting with. Gentle, patient, and oddly generous. So let us start somewhere familiar. Think, for a moment, about a candle. Not a special candle, just an ordinary one on a kitchen table, the kind you might light during a power cut or set beside a plate at dinner. You light it, and the flame steadies itself, and for a while it seems almost permanent. It flickers a little, it leans when you walk past, but it holds its shape. You could leave the room, make a cup of tea, come back, and it would still be there, burning quietly, as if it had been doing so forever. But of course, it has not been burning forever, and it will not. The candle is spending itself the whole time you watch it. The wax is the fuel, and the flame is slowly drinking it, drawing it up through the wick, turning it into light and warmth, and a thin curl of smoke. The reason the flame looks so steady is that the spending is happening at a rate you cannot see. The candle is dying from the very first second you light it. It is just dying at a speed that suits a human evening, a few hours from match to puddle. A star is doing almost exactly this, only on a scale that is hard to hold in the mind. A star is a flame. It has fuel, and it is spending that fuel. And the steady shining we see is the shining of something that is using itself up. The difference is the rate. Where a candle measures its life in hours, a star measures its life in millions or billions or trillions of years. And the size of the star, the amount of wax, if you like, decides not only how long it burns, but how it goes out at the end. That is the quiet thread we will follow tonight. Mass is fate. How heavy a star is born decides almost everything about how it will die. Now, here is the question that sits underneath the whole story, and I want to lay it out plainly before we go any further, because once you have it, everything else hangs from it. A star is enormous. The Sun, which is a fairly average star, holds well over 1 million times the volume of the Earth. It is a vast ball of gas, and gas wants to spread out, to drift apart, to fill whatever space it can. So you might expect a star simply to puff away into nothing, like steam off a kettle. But it does not. It holds together, a tight, glowing sphere, for billions of years. Something is pulling it inward and holding it firm. That something is gravity. Every part of the star pulls on every other part. All that mass, all those layers of gas, are forever falling toward the center, trying to crush the star down into a smaller and smaller point. And here is the thing that makes a star, the balance that defines its entire existence. If gravity is forever trying to crush the star inward, then something must be forever pushing back outward, holding the walls up, or the whole thing would have collapsed long ago. A star is a slow, patient war between two forces. Gravity pulling in, something else pushing out. And a star dies, in every single case we will talk about tonight, at the moment that war is finally lost. So what is doing the pushing? What holds the star open against its own enormous weight? To answer that, we have to go back, not in the life of the star, but in the life of people. Because for most of human history, nobody had any idea what a star was made of, or why it shone, or whether it could ever stop. And the slow, patient uncovering of that answer is a story full of real people, sitting in real rooms, often being told they were wrong. Let us go back to the early 1800s, to a workshop in Bavaria, in what is now part of southern Germany. There is a young man there named Joseph von Fraunhofer, born in 1787. His early life was hard. He was orphaned as a boy and apprenticed to a glassmaker. And when he was 14, the workshop he lived in collapsed and buried him in the rubble. He survived, and the prince who helped dig him out gave him books and time to study. And Fraunhofer turned out to have a rare gift for glass and for light. He became the finest maker of optical glass in the world, the kind used in telescopes and surveying instruments. And in the course of perfecting his lenses, he did something almost by accident that would echo for the next 2 centuries. He passed sunlight through a narrow slit and then through a prism, spreading it out into a rainbow, the way a prism always does. But Fraunhofer looked more carefully than anyone had before, with better glass than anyone had owned before. And in that smooth band of color, he saw lines, thin, dark lines, scattered across the spectrum like the gaps between fence posts. He counted hundreds of them. He measured their positions with great care. He had no idea what they were, but he knew they were real, and he knew they were always in the same places. This was around 1814. Those dark lines still carry his name. We call them Fraunhofer lines. Now, slow down for a moment, because this is one of those quiet turning points that does not look like much at the time. A few dark lines in a rainbow. But those lines are a message. They are, it turned out, a kind of fingerprint. And the fingerprint belongs to the elements inside the sun. Each kind of atom, hydrogen, sodium, iron, calcium, absorbs light at its own particular set of colors, leaving its own particular pattern of dark gaps. So those lines were the sun telling us, in a code nobody could yet read, exactly what it was made of. Fraunhofer had found the message. He died young, at 39, in 1826, of the lung trouble that plagued glassworkers of his time, long before anyone understood what he had really seen. It took the rest of the century to learn to read the code. 2 more men in Germany, Gustav Kirchhoff and Robert Bunsen, the Bunsen of the burner you may have used in a school laboratory, worked out in the 1850s and 60s that you could match those dark lines to the bright lines that elements give off when you heat them in a flame. Heat sodium, and it glows a particular orange. Look at the sun, and there is a dark line at exactly that orange. Therefore, There is sodium in the sun. Suddenly, the stars were not unreachable. You did not have to travel to them. Their light arrived carrying a written account of their ingredients, and we had finally learned the alphabet. But knowing what the sun was made of is not the same as knowing why it shines. And here, the story takes a strange and human turn that I find genuinely touching. Because when people finally worked out what stars were mostly made of, almost nobody believed it, including, at first, the woman who discovered it. Her name was Cecilia Payne, later Cecilia Payne Gaposchkin, and she was born in England in 1900. She went to Cambridge, where she completed all the requirements for a degree. But Cambridge would not actually grant degrees to women at the time, so she left, the way many brilliant women of that era were quietly forced to leave. She crossed the Atlantic to the Harvard College Observatory in the United States, where a remarkable group of women had been doing the painstaking work of cataloging the stars. One of them, Annie Jump Cannon, born in 1863, had personally classified hundreds of thousands of stars by their spectra, sorting them into the sequence of letters that astronomers still use today. The way students remember that sequence is with the phrase, "Oh, be a fine girl, kiss me." The letters O, B, A, F, G, K, M, standing for stars from the hottest blue down to the coolest red. Our sun is a G, sitting comfortably in the middle. I want to pause here and stay with those women a little longer, because they are too often left as a footnote, and the room they worked in deserves to be seen. At the Harvard College Observatory, around the turn of the 20th century, the director, Edward Pickering, had hired a group of women to do the painstaking work of measuring and classifying stars from photographic plates. They were called, in the language of the time, computers, because computing is what they did by hand, hour after hour, star after star, in a long room full of glass plates and careful handwriting. They were paid very little, far less than a man would have been, and many of them had been quietly turned away from the universities that should have welcomed them. And yet from that room came some of the most important discoveries in the history of astronomy. One of them was Williamina Fleming, a Scottish woman who had come to the United States, been abandoned by her husband, and taken work in Pickering's own household as a maid before he noticed her sharpness and moved her to the observatory. She went on to classify tens of thousands of stars and to discover the strange object we now call the Horsehead Nebula. Another was Henrietta Swan Leavitt, born in 1868, who was deaf for much of her life and who studied a particular kind of star that pulses, brightening and dimming on a steady cycle. She discovered, around 1908, that the slower one of these stars pulses, the brighter it truly is. That single quiet finding became the measuring stick astronomers would later use to gauge the distance to far-off stars and galaxies, and even, eventually, to weigh the size and the age of the universe. She did it on a clerk's wage, and she did not live to see how much the world would lean on her result. And the very idea that a star might change at all, might brighten or dim rather than burning forever at a fixed and eternal light, has its own gentle history. Long before any of this, an English astronomer named John Goodricke, who was deaf and who died tragically young at only 21 in 1786, had carefully watched a star called Algol in the constellation we call Perseus. He noticed that it dimmed and brightened on a strict schedule every few days, and he proposed, correctly, that a darker companion must be passing in front of it. He was a teenager working it out by patient eye, and he was right. The point I want you to feel is this. For most of human history, people assumed the stars were changeless, fixed, and permanent, the one part of the world you could rely on, never to alter. It took centuries of careful, humble watching, much of it by people the world overlooked, to notice that the stars do change. They flicker, they pulse, they are born, and they age. And one day, every one of them, they die. Cecilia Payne took all that careful classification and asked a deeper question. Not just how the stars sorted themselves, but what their spectra revealed about their actual composition. And in her doctoral thesis, in 1925, she came to a conclusion that was, by the standards of the time, almost unthinkable. The stars, she found, were overwhelmingly made of hydrogen, the lightest element of all, and after that, helium. Not iron, not the rich mix of heavier elements that made up the Earth. The stars were nearly all hydrogen. This is where I want you to feel how strange that was to the people who first heard it. Everyone had assumed that the sun, being a serious and important object, would be made of serious and substantial stuff, much like the Earth. The idea that it was almost entirely the lightest, wispiest gas seemed absurd. A senior astronomer named Henry Norris Russell, who was respected and powerful and not unkind, told her the result must be wrong. And under that pressure, she added a line to her thesis, calling the hydrogen finding almost certainly not real. She was right, and she had been talked out of it. A few years later, Russell did the calculation himself, found the same answer, and published it. And for a long time, he got most of the credit. Her thesis has since been called one of the most brilliant ever written in astronomy. She eventually became the first woman to be a full professor in her department at Harvard, and the first to chair it, though that recognition came slowly, decades later. So by the 1920s, we knew that stars were mostly hydrogen. And that is the key that unlocks the puzzle of why they shine, and therefore how they die. Because hydrogen, it turns out, is fuel, the lightest, most abundant fuel in the universe. Let me explain what is happening in the heart of a star as simply as I can, and we will build the detail up slowly, one layer at a time, the way you would add logs to a fire. A star is a ball of hydrogen gas so massive that its own gravity squeezes the center to an unimaginable pressure and temperature. We are talking about a core hotter than 15 million degrees, with the weight of the entire star pressing down on it. And under those conditions, something remarkable happens to the hydrogen. The atoms are pressed so hard, so close, so fast, that their nuclei begin to stick together. Hydrogen nuclei fuse, merging in stages into helium. And when they merge, a tiny fraction of their mass vanishes and reappears as energy. An enormous amount of energy from a very small amount of mass. That is the secret. That is the candle flame. A star shines because deep in its core, hydrogen is being welded into helium, and every welding releases a flash of energy that works its way, slowly, outward to the surface and into the night, where some of it, after a very long journey, lands gently on your eyes. Let me slow down on that journey for a moment, because it is one of the gentlest facts I know, and it is a lovely thing to drift toward as you settle. The welding is not a single dramatic event, but a patient chain. In a star like the Sun, 4 hydrogen nuclei, 4 simple protons, find their way together in stages. 2 of them stick and 1 quietly transforms, and the pair becomes a heavier form of hydrogen. That heavier hydrogen catches another proton and becomes a light form of helium. And finally, 2 of these light helium nuclei meet and combine, shedding a couple of protons back into the mix. And the result is 1 ordinary helium nucleus, where 4 hydrogen nuclei used to be. It sounds fiddly, and it is. And it happens trillions upon trillions of times every second in the heart of the Sun. The whole long process has a name. the proton-proton chain, and you do not need to remember it. You only need the picture. 4 light things going in, 1 heavier thing coming out, and a small spark of energy released each time, because the helium that comes out weighs very slightly less than the 4 hydrogen pieces that went in. That missing weight, less than 1% of it, becomes the light. Now here's the part I find almost unbearably gentle. That spark of energy is born in the very center of the star as a tiny flash of light, and it then has to get out. But the inside of a star is not empty space. It is packed almost solid with particles, so densely that the little flash of light cannot fly straight out the way sunlight crosses a room. Instead, it travels a hair's breadth, bumps into a particle, gets absorbed, gets spat out again in some random new direction, travels another hair's breadth, and bumps again. It staggers outward like someone trying to cross a crowded hall in the dark, taking one tiny step, being turned around, taking another. And because it is forever being knocked off course, the journey from the core of the sun to its surface, a distance light could cross in just over 2 seconds if the way were clear, actually takes, by many estimates, tens of thousands of years. Some put it at 100,000 or more. Sit with that. The warmth that fell on your face the last time you stood in the sun was, in a sense, ancient. The energy in it was forged in the sun's core, back when the earth looked utterly different, when great sheets of ice still lay across the northern world, when no city had yet been built. It spent all those long ages staggering outward through the body of the sun, and only in the final 8 minutes did it leap across the empty space between the sun and the earth and arrive, fresh-seeming, on your skin. Every sunbeam is older than human history. That is what a star shining really is. A slow, patient leaking out of energy that was made long ago and has been trying to escape ever since. Now here is the part that ties it back to the war between gravity and pressure. All that energy pouring out from the core does more than make light. It makes heat, and heat makes the gas push outward. The fusion in the center is what holds the star open. It is the outward shove that balances gravity's inward pull. The star is shining and holding itself up by the same act. As long as it has hydrogen to fuse in its core, it can keep the war in a perfect, gentle stalemate. It shines, it holds its shape, and it feels, from the outside, eternal. The way that candle felt steady on the table. We call this long, stable stretch of a star's life the main sequence, and it is by far the longest chapter for almost every star. Our sun has been on the main sequence for about 4.5 billion years, quietly fusing hydrogen into helium in its core, and it has roughly 5 billion years left before that fuel runs low. 10 billion years, more or less, of steady shining. That is one candle, and it is barely halfway burned. Before we meet the men who finally understood the fire, it is worth sitting with how badly it once stumped the cleverest people alive. Because the wrong answer was reasonable, and the argument it caused is one of the great quarrels in the history of science. Through the 1800s, nobody knew what kept the sun burning. A coal fire could not do it. If the sun were made of the finest burning coal imaginable, it would have turned to ash in a few thousand years, and it had plainly been shining far longer than that. So the finest physicists of the age reached for the most powerful source of energy they knew, which was gravity itself. The idea, developed by the German physician and physicist Hermann von Helmholtz and refined by the formidable British physicist William Thomson, later known as Lord Kelvin, was that the sun shines by slowly shrinking. As the vast ball of gas contracts under its own weight, the falling matter releases heat the way a weight dropped to the floor gives up its energy in the thud. A sun slowly settling inward could, they calculated, glow for a good long while from that alone. It was clever, It used real physics, and it gave a definite answer for how old the sun could be. The trouble was the number. Their mechanism could only keep the sun shining for something like 20 or 30 million years. Beyond that, the well of gravitational energy would run dry. Now here is where the quarrel began, and it is a wonderful one. 20 or 30 million years sounds like a great deal, but to the geologists of the same century, men patiently reading the slow layering of rock and the carving of valleys, it was nowhere near enough. The Earth, the rocks insisted, had to be far older, hundreds of millions of years at the very least. And to a quiet naturalist named Charles Darwin, who needed immense stretches of time for life to change and branch into the living world we see, a young sun was a serious problem, and Kelvin's confident figure troubled him deeply. So you had the physicists, armed with the certainty of their equations, telling the geologists and the biologists that the sun and the earth simply could not be as old as the rocks and the living things appeared to demand. Both sides were careful. Both sides were honest. And one of them was missing something enormous. What they were missing, of course, was the fire we now understand. There was a source of energy in the sun, millions of times more potent than gravitational shrinking, one nobody could have guessed at in Kelvin's day, because it lived inside the atom, in the welding of hydrogen into helium. Once that was grasped, in the early 20th century, the puzzle dissolved. The sun was not 20 million years old. It was billions of years old, with billions more ahead of it. And the geologists and Darwin had been right all along. Kelvin, brilliant as he was, had been defeated not by a flaw in his reasoning, but by the existence of a kind of energy he had no way to know about. There is a gentle lesson folded into that, about the difference between an argument that is wrong and an argument that is merely incomplete, and about how the universe so often turns out to be stranger and more generous than our best guesses allow. The two men who first really understood the fire are worth meeting. Arthur Eddington, born in 1882, an English astronomer of great authority and great imagination, argued in the 1920s that the sun must be powered by the fusing of hydrogen into helium, even though nobody yet knew the detailed mechanism. When a colleague objected that the sun was not hot enough for atoms to overcome their mutual repulsion, Eddington is said to have replied, with some impatience, that the critic should go and find a hotter place. The actual step-by-step machinery was worked out at the end of the 1930s, most completely by Hans Bethe, a German-born physicist who had fled to America. In a famous paper in 1939, he described the chains of reactions by which stars turn hydrogen into helium, and he won the Nobel Prize for it many years later, in 1967. So now we had the whole picture. A star is hydrogen, fusing into helium, the fusion holding back gravity, the balance lasting for as long as the fuel holds out. There is one more thread to add here before we move on, and it matters for everything that follows. So let me lay it down gently. Bethe found that stars actually have two different ways of welding hydrogen into helium. The first is the patient proton-proton chain we just walked through, the one that powers calmer, cooler stars like our sun. But in hotter, heavier stars, a second method takes over, a faster one, in which carbon, nitrogen, and oxygen act as a kind of go-between, passing protons along an assembly line and emerging unchanged at the end, ready to do it again. It is called the carbon-nitrogen-oxygen cycle, and the same physicist who pieced together the proton-proton chain helped describe it, alongside the German physicist Carl von Weizsäcker, working independently around the same time. You do not need to hold the chemistry. You only need one consequence of it. This second method runs far hotter and far faster. So the more massive a star is, the more fiercely it burns, the brighter it blazes, and the sooner it spends itself. And that is why mass decides everything. A small star sips its fuel and lasts almost forever. A giant star gulps it down and is gone in a geological instant. The same logic that lets a red dwarf shine for trillions of years condemns a blue giant to burn out in a few million. They are running the same fire, hydrogen into helium, but at wildly different speeds, and the speed is set by how much weight is pressing down on the core. Heavy stars live fast. Light stars live slow. Keep that one sentence with you, because it is the key to every death we are about to walk through. Which brings us, at last, to the real subject of tonight. The fuel does not hold out forever. And what happens when it runs low depends entirely on how heavy the star was to begin with. So let us take the deaths one at a time, starting with the gentlest, the slowest, the most patient deaths of all, and working our way up toward the violent and the strange. Let us begin with the smallest stars. The red dwarfs. If you went out tonight and looked up, you would not see a single red dwarf with your naked eye, not one, even though they are by far the most common kind of star in the universe. Roughly 3 out of every 4 stars are red dwarfs. They are everywhere, and they are invisible to us, because they are so dim. A red dwarf might be only 1/10 or 1/5 the mass of the sun, and it might shine with less than 1,000th of the sun's light. They are the embers of the cosmos, the small, dull red coals, and there are vast numbers of them tucked into the dark. You might think that a small star with so little fuel would burn out quickly. The opposite is true, and the reason why is one of the loveliest facts in all of astronomy. Stay with me through this, because it is a little counterintuitive, and it rewards a slow look. A big star has a lot of fuel, but it also burns ferociously, because the crushing weight of all that mass drives the core to enormous temperatures, and the fusion races along. A small red dwarf has little fuel, but it also burns very, very gently because its modest gravity keeps the core relatively cool. So the fusion proceeds at a crawl. And there is a second gift. A small star is what we call fully convective. Its insides churn and roll over and over, like a pot of thick soup simmering slowly, so that fresh hydrogen from the outer layers keeps getting carried down into the core to be used. The sun cannot do this. The sun burns only the hydrogen near its center and never touches most of its fuel. But a red dwarf stirs itself constantly and can eventually burn nearly all the hydrogen it has. Put those two things together, a slow burn and complete use of the fuel, and you get lifetimes that simply do not fit inside any ordinary sense of time. A red dwarf can keep shining for hundreds of billions of years. The smallest ones may last for trillions of years, perhaps as long as 10 trillion years or even more. And here is the part that I find quietly staggering. So let me say it plainly. The universe itself is only about 14 billion years old, which means that not a single red dwarf in the entire universe has ever died. Not one has even finished its main life. Every red dwarf that has ever existed is still out there, still burning, still in the long, slow morning of its existence, with almost all of its life ahead of it. We have never seen one of these gentle stars die, and we never will, because their deaths lie unimaginably far in the future, long after our own sun is gone, long after the Earth is gone. So how do we know what their deaths will look like? We work it out the way you might predict the last act of a play you have to leave early, by understanding the characters and the logic of the story. The physics tells us what must happen, even though we cannot wait around to watch. When a red dwarf finally exhausts its hydrogen, trillions of years from now, The fusion in its core will sputter and fail, and the gentle outward push will fade. Gravity, which has been waiting patiently the whole time, will begin to win. The star will shrink, but a red dwarf is too small to ever reach the temperatures needed to fuse the helium ash it has built up, so it cannot light a second fire. It simply contracts, slowly, releasing the last of its stored heat. Some calculations suggest it may even pass through a phase of glowing a steadier blue as it shrinks and its surface concentrates. A so-called blue dwarf, an object no human or any other being has ever seen, because the universe has not yet aged enough for even one to exist. And then, at last, it settles into a small, dense, slowly cooling ember, called a white dwarf, made mostly of helium, no bigger than the Earth, glowing fainter and fainter for ages beyond counting until it is finally dark. That is the quietest death there is. No explosion, no drama. Just a slow fade, over a span of time so vast that the entire history of the universe so far is only a fraction of a single % of it. When you picture a red dwarf dying, picture the very last coal in a fireplace at the end of a long winter night, the one that holds a soft orange glow for hours after everyone has gone to bed, dimming so gradually that you could never name the moment it went out. That is a red dwarf. That is the gentlest goodbye in the sky. And here is something to make these dim, patient stars feel close rather than distant. The very nearest star to our own sun, the closest other star in all the universe, is a red dwarf. Its name is Proxima Centauri, and it sits a little over 4 light-years away, which sounds near in cosmic terms and is in truth a distance so vast that our fastest spacecraft would take tens of thousands of years to reach it. It was first identified in 1915 by a Scottish astronomer named Robert Innes, working in South Africa. And despite being our nearest stellar neighbor, it is far too faint to see with the naked eye. You could stand out under a perfect dark sky, look straight toward it, and never know it was there. We now know it has at least one planet circling it, found in 2016, a world roughly the size of the Earth, sitting in the gentle zone where liquid water might be possible. Whether anything lives there, we have no idea. But it is a quiet thought, that our closest neighbor in the whole sky is one of these dim, long-lived embers, the kind of star that will still be shining long after the sun is a cold cinder. Red dwarfs are not entirely peaceful, mind you. For all their dimness, many of them are prone to sudden, violent flares, brief flashes where the star briefly brightens as magnetic energy snaps and releases, the way a calm pond can throw up a surprising splash. For any life on a planet circling such a star, those flares would be a serious problem, scouring the surface with radiation. So even the gentlest stars have a temper. But the deep truth about red dwarfs is their patience. As the ages roll on and the universe grows old, the big bright stars will all burn out first. The sun-like stars will follow. And in the unimaginably distant future, when the sky has gone mostly dark, it will be the red dwarfs that are still burning, the last stars left, holding their small, steady lights against the growing night, long after everything else has gone out. Now let us move up the scale, to a star like our own. A yellow star, the kind of death that, in about 5 billion years, will come to our own sun, and that you can therefore think of, in the very gentlest way, as the death of the star that made you. A star like the sun spends its 10 billion years or so fusing hydrogen into helium in its core, exactly as we described. But helium is heavier than hydrogen, and it sinks and gathers at the very center, building up like ash at the bottom of a grate. And helium, under these conditions, will not burn. The core temperature is high enough to fuse hydrogen, but not yet high enough to fuse helium, which needs even fiercer heat. So as the eons pass, the core fills with helium ash that just sits there, inert, useless, dead weight. Here is where the story turns. And it turns in a way that is genuinely surprising the first time you hear it. So let us go through it slowly. You might expect that as the star runs out of fuel, it would cool down and dim and shrink. That is what a fire does. But a star does the opposite. As the spent helium core grows and the hydrogen fire moves into a thin shell around it, the core, with no fusion to hold it up, begins to contract under gravity. And as it contracts, it heats up. And that extra heat pours into the shell of hydrogen still burning around it, and the shell burns harder than ever, fiercer than the original core fire ever was. The star pours out more energy than it did in its whole stable life. And all that extra outward push does something dramatic to the outer layers. It inflates them. The star swells and swells and swells, ballooning outward to dozens or even 100 times its original size. And as the surface spreads over that vast new area, it cools and reddens, the way a coal you blow on glows brightest at its heart, but looks dull and red at the edges. The star has become a red giant. When our sun does this, the consequences for our own world are not subtle. The sun will swell so large that it will swallow Mercury. Then Venus and its glowing surface may reach out toward the orbit of the Earth itself. Long before that, the rising heat will have boiled away the oceans and stripped the air. This is not something to be frightened of tonight. It lies 5 billion years off, and human beings, and very probably any descendants of human beings, will be an unimaginably old memory by then, if they remember anything at all. But it is worth pausing on, because it is the literal future of the warm point of light that every living thing on this planet has depended on for its entire history. The same sun that is setting somewhere on the Earth right now, while you settle in, will one day become a red giant and end the world. Slowly, patiently, like everything else in this story. Now, inside that swollen red giant, the contracting helium core keeps heating, and finally it crosses the threshold. The helium ignites. In a star like the sun, this happens with a sudden flash, a brief, fierce flare of fusion deep in the core called the helium flash, where, in a matter of minutes, the core releases a burst of energy. From the outside, you would notice almost nothing, because all that energy goes into rearranging the star's interior rather than into extra light. But inside, a new fire has been lit. The star now fuses helium into carbon and oxygen, building heavier ash in its core, and it settles for a while into a new, briefer, stable life, burning helium the way it once burned hydrogen. But a sun-like star is not heavy enough to take the next step. Once it has filled its core with carbon and oxygen, it cannot squeeze hard enough to fuse those in turn. The fire is running out of things it can burn. And so the star approaches its end, not with a bang, but with something far gentler and, to my mind, far more beautiful. The outer layers of the dying star have grown loose and bloated, only weakly held by the star's diminished grip. Pulses of energy from the struggling core ripple outward, and with each pulse the star sheds another veil of gas into space. Over tens of thousands of years, the star gently breathes its entire outer atmosphere away, layer by glowing layer, until all that is left exposed is the hot, dense core at the center. And that core, still searingly hot, lights up the expanding shells of gas it has just exhaled, making them glow in delicate rings and shells and butterfly shapes, lit from within in greens and blues and reds. These glowing shrouds are among the most beautiful objects in the night sky, and we have, by a small accident of history, a slightly odd name for them. We call them planetary nebulae. They have nothing to do with planets. The name comes from the 1700s, when the astronomer William Herschel, the same man who discovered the planet Uranus, peered at these soft, round, glowing objects through his telescope and thought they looked like the dim disk of a planet rather than a sharp point of starlight. The name stuck even after we understood that these were not planets at all, but the exhaled atmospheres of dying stars. So when you hear planetary nebula, set the word planet gently to one side. What you are really looking at is a star's last breath, made visible, hanging in space and glowing for a few thousand years before it disperses into the dark. And the core left behind, that bare, hot, exposed heart of the star, made of carbon and oxygen, squeezed by gravity into a sphere about the size of the Earth, but holding nearly the mass of the Sun. That is a white dwarf. The same endpoint we met with the red dwarf, only this one is made of heavier ash, and it is born hot rather than cool. I want to dwell on a white dwarf for a moment, because it is one of the strangest and most important objects in this whole story, and understanding it will help us understand the violent deaths still to come. Imagine taking the entire mass of the Sun, all of it, and packing it into a ball no larger than the planet you are lying on right now. The matter inside a white dwarf is crushed to a density that is almost impossible to picture. A single spoonful of it would weigh as much as a small truck. And here is the question that puzzled astronomers when they first found these objects. If gravity has crushed the star down this far, and there is no fusion left to push back, no fire holding it open, then what is stopping it from collapsing further? What holds a white dwarf up? The first white dwarf anyone really understood was the faint companion of the bright star Sirius, the brightest star in our night sky. Back in 1844, the German astronomer Friedrich Bessel noticed that Sirius wobbled slightly as it moved across the sky, as though something unseen were tugging on it. He predicted a hidden companion. In 1862, an American telescope maker, Alvin Graham Clark, testing a new lens, actually saw it. A tiny dim point beside the dazzling Sirius. We call it Sirius B. And in 1915, the astronomer Walter Adams measured its light and realized something impossible seeming. This faint little star was as massive as the Sun, but as small as a planet. It was the first white dwarf to be recognized for what it was. Nobody yet had any idea what could hold such a thing up. The answer came from a brilliant young man on a long sea voyage, and his name takes us into the heart of how the most violent stellar deaths happen. So let me introduce him properly, because he matters enormously for the rest of tonight. His name was Subramanian Chandrasekhar. He was born in 1910 in what was then British India, into a family of scholars, and he was extraordinarily gifted in mathematics from a young age. In 1930, at the age of 19, he won a scholarship to study at Cambridge in England, and he boarded a steamship for the long voyage from India to Britain. And on that voyage, with little to do but think, he worked out something profound about white dwarfs, something that would not be fully accepted for decades, and that would change our understanding of how stars die. To explain what he found, I need to give you one strange idea. Gently, and then a plain language version right after, the way I promised at the start. The idea comes from quantum physics, and it is called degeneracy pressure. Here is the technical version first. Electrons, the tiny particles that swarm around atoms, refuse to be packed too closely together in the same state. There is a rule in nature that forbids it. So when you crush matter hard enough, the electrons themselves resist, not because they repel each other in the ordinary way, but because the universe simply will not allow them to occupy the same space and motion at once. That resistance creates a pressure, and that pressure can hold up an entire star. Now here is the plain language version, the one to actually hold in your mind as you drift. Imagine a crowded train carriage at rush hour. People will squeeze together to a point, shoulder to shoulder, but there comes a moment when the carriage is genuinely full, and no one can be pushed any closer, no matter how hard the doors try to close. The crowd pushes back simply by being a crowd that cannot be compressed any further. That stubborn refusal of a packed crowd to be squeezed is more or less what holds a white dwarf up. The electrons inside it are packed as tight as nature allows, and their refusal to be packed any tighter is the force that balances gravity. It is not fire. It is not heat. It is the sheer impossibility of squeezing them closer. A white dwarf can therefore hold its shape forever, even with no fuel left, cooling slowly over billions and trillions of years toward darkness. But here is what Chandrasekhar realized on that ship. And this is the hinge on which the whole rest of the story turns. That stubborn crowd has a limit. If you pile more and more mass onto a white dwarf, gravity grows stronger, and eventually it grows so strong that even the packed crowd of electrons cannot hold the line. There is a maximum mass that a white dwarf can possibly have. Above that mass, the electron crowd gives way, and the star cannot save itself. Chandrasekhar calculated that limit. It comes out to about 1 4/10 times the mass of the Sun. We call it, today, the Chandrasekhar limit. A white dwarf below it survives forever. A core pushed above it is doomed to collapse. When Chandrasekhar presented this in the 1930s, the most powerful astronomer in Britain, the very same Arthur Eddington we met earlier, the man who had championed fusion in stars, stood up in a meeting in 1935 and ridiculed it. He could not accept that nature would allow a star to collapse so completely, and he said so publicly, in a way that wounded the young Chandrasekhar deeply. Eddington was wrong, and Chandrasekhar was right, and the limit bears Chandrasekhar's name. But it took years for the field to come around, and Chandrasekhar eventually left England and built his long, distinguished career in the United States, at the University of Chicago. He won the Nobel Prize in 1983, nearly half a century after the voyage on which a teenager worked out the fate of dying stars. There is a deep human lesson tucked into that delay about how long it can take for a true thing to be believed. But we will leave that thought to settle on its own. So we now have our first 2 deaths. The red dwarf, fading slowly to a cool ember. The sun-like star swelling, exhaling a glowing nebula, and leaving a white dwarf held up forever by the stubbornness of its electrons. Both of those are gentle deaths. But before we leave the white dwarf behind, I have to tell you about a twist, because a white dwarf does not always get to rest in peace. Sometimes it dies a second time, and the second death is anything but gentle. So let us slow down for this, because it is one of the stranger turns in the whole story. Picture a white dwarf, that small, dense, Earth-sized ember, the burnt-out heart of a sun-like star, cooling quietly in the dark. Now suppose it is not alone. Most stars, it turns out, are born in pairs, 2 stars circling one another. And if one of them dies and leaves a white dwarf behind while the other is still alive and shining, you have a white dwarf locked in orbit with a living companion. And here is where the trouble begins. The white dwarf, dense and grasping, can begin to pull gas off its neighbor, drawing a steady stream of fresh material onto itself. Slowly, over time, it gains weight. And remember what Chandrasekhar found on that ship. A white dwarf can only hold so much. There is a limit, about 1 4/10 times the mass of the Sun, above which the electrons can no longer hold the line. So picture this doomed little star creeping toward its limit, gaining mass it cannot afford. As it approaches that fatal weight, the pressure and heat in its center climb, and the carbon and oxygen it is made of, which had been sitting there inert for ages, suddenly reach the point where they can fuse. But there is nothing to hold this fire in check. In an ordinary star, if the core gets hotter, it expands and cools itself and settles down. A white dwarf cannot do that, because of the strange way its packed electrons hold it up. So the fusion, once it starts, runs away completely. In a matter of seconds, a wave of runaway burning tears through the entire white dwarf, fusing its carbon and oxygen all at once, and the whole star detonates. Not the outer layers, not part of it, the entire star. It is utterly destroyed, blown apart so completely that, like the rarest titans we will meet later, it leaves nothing behind at all. No white dwarf, no neutron star, no black hole, just an expanding cloud and an empty place where a small dead star used to be. We call this a Type 1 a supernova, and it has a beautiful and useful peculiarity. Because every white dwarf detonates at almost exactly the same weight, that same Chandrasekhar limit, every one of these explosions shines with very nearly the same true brightness. They are like identical light bulbs scattered across the universe. And if you know how bright a light bulb really is, then by seeing how dim it looks from where you stand, you can work out exactly how far away it is. Astronomers use these exploding white dwarfs as measuring beacons, as a way to gauge distances across billions of light years of space. And in the late 1990s, two teams of astronomers, led by Saul Perlmutter, Brian Schmidt, and Adam Rees, used these very explosions to measure how the expansion of the universe was changing over time. They expected to find it slowing down. Instead, to their astonishment, they found it speeding up. The universe is not just expanding, but expanding faster and faster, driven by something we still do not understand and have given the placeholder name dark energy. They won the Nobel Prize for it in 2011. And it all rested on the deaths of small, quiet stars. White dwarfs pushed one grain too far, detonating across the cosmos and lighting the way for us to read the fate of everything. The gentlest deaths, it turns out, can tell us the largest truths. Now we cross a line into the deaths of heavy stars, and the gentleness ends. Let us talk about what happens when a star is born big. 8 times the mass of the sun, or 10 times, or 20, or 40. These stars are rare, but they are the engines that built much of the universe, and they die in a way that is one of the most violent events in all of nature. A massive star lives fast. With so much weight pressing on its core, the temperature there is fearsome, and the fusion races. A star 10 or 20 times the mass of the sun might burn through its entire supply of hydrogen in only a few million years, rather than the sun's 10 billion. It blazes blue-white and brilliant and brief, like a candle held too close to the flame, burning down in a fraction of the time. And when its core hydrogen runs out, it does not stop, the way a small star does. It is heavy enough to keep going. This is the part of the story I love most. So let me lay it out carefully, because it builds toward the moment everything changes. When a massive star exhausts the hydrogen in its core, the core contracts and heats, just as in the sun. But here the temperature climbs so high that it ignites the helium ash and begins fusing it into carbon. And when the helium runs out, the core contracts and heats again, hotter still. And now it can fuse carbon into heavier elements, neon and oxygen and magnesium. And when those run low, it contracts and heats again, and fuses those into silicon. And the silicon, contracting and heating one final time, fuses into iron. Picture what this does to the inside of the star. It builds up in layers, like the rings of an onion, or the layers of a very strange cake. At the outside, a shell of hydrogen still burning. Beneath it, a shell of helium. Beneath that, carbon, then oxygen, then neon, then silicon, each shell hotter and denser than the one above it, each fusing into the next. And at the very center, a growing core of iron. The whole star, in its final days, is fusing furiously in concentric shells around an iron heart. And I want you to feel how fast all of this happens at the end, because the acceleration is one of the most dramatic things in nature, and it is strangely easy to drift along with. Remember that a massive star spends millions of years burning hydrogen, the long, calm chapter of its life. When that runs out and it begins burning helium, that stage lasts only a few 100,000 years, a small fraction of what came before. Then the helium is gone and it starts on carbon, and the carbon burning stage lasts perhaps a few hundred years. A few hundred years, where the first stage took millions. Then carbon gives way to neon, and the neon burning stage lasts only about a year. Then oxygen, and that burns for a matter of months. And then silicon, the very last fuel before iron, and the silicon burning stage lasts about a single day. One day. Let that sink in slowly. A star can shine steadily for millions of years, and then, in its final week, it races through its last fuels faster and faster, like a stone rolling downhill that picks up speed as it falls, until in the final day, it is fusing silicon into iron at a furious pace, building that doomed iron core grain by grain, completely unaware, if a star could be aware of anything, that it has only hours left. From the outside, you would notice nothing. The star looks the same on the morning of its last day as it did 1,000 years before. But deep in its heart, the clock has nearly run out, and the long, patient balance that is held for the entire life of the star is about to be lost in less than a second. There is something almost unbearably quiet about that image. A vast, brilliant star, going about its final day exactly as it went about all the days before, with the catastrophe already loaded and waiting in its core. And here we arrive at the single most important fact in the death of massive stars, the fact that turns a shining star into a catastrophe. So let us slow right down for it. Iron is the end of the road. You cannot get energy by fusing iron. Think about why a star shines in the first place. When light elements fuse into heavier ones, a tiny bit of mass turns into energy, and that energy is what holds the star up and makes it shine. That is true all the way up the ladder, from hydrogen to helium to carbon and onward, each step releasing energy. But iron is special. Iron sits at the very bottom of a kind of energy valley. It is the most stable nucleus there is, in the sense that matters here. To fuse iron into anything heavier does not release energy. It absorbs it. Iron is ash that cannot be burned. When a star builds an iron core, it has finally run out of any fuel that can hold it up. The fire that has been pushing outward against gravity for millions of years has nothing left to burn. And now the war between gravity and pressure, which the star has been winning its whole life, is lost in an instant. And I mean an instant, almost literally. Once the iron core grows past the Chandrasekhar limit, that same one in 4/10 solar masses Chandrasekhar found on his ship, the electrons can no longer hold it up, and there is no new fire to light. Gravity, free at last, crushes the core inward, and it happens with breathtaking speed. The core of the star, an iron ball larger than the Earth, collapses in less than a single second. The inner part falls inward at 1/4 of the speed of light. The temperature soars. The electrons are crushed into the atomic nuclei, merging with protons to form neutrons, and a flood of ghostly particles called neutrinos pours out, carrying away an enormous amount of energy. In that instant, a structure the size of a planet becomes a ball perhaps 20 kilometers across, the size of a city. And then something extraordinary happens. The collapsing core suddenly stops, hard when it reaches a new kind of wall, and it bounces. The infalling outer material slams into this newly rigid core and rebounds, and a shock wave tears outward through the star. Driven and reheated by that vast flood of neutrinos, the shock blows the entire outer body of the star apart in a titanic explosion. For a few weeks, that single dying star shines as brightly as 100 billion ordinary stars put together. It can briefly outshine its entire galaxy. We call this a supernova. Try, for a moment, to hold the scale of that. A galaxy contains hundreds of billions of stars, and for a few weeks, one single star, in its death, can shine nearly as bright as all the rest of them combined. If you could stand at a safe distance and watch, you would see a point of light flare up out of nowhere, swelling over days into a brilliance that floods the dark, and then fading, slowly, over weeks and months, as the explosion expands and cools. In that one event, the star releases more energy than the sun will produce in its entire 10 billion year lifetime, all of it poured out in a matter of weeks. It is, by a wide margin, one of the most violent and luminous things the universe knows how to do. This raises a question people often ask once they understand it, and I will answer it gently because the answer is reassuring. Could a supernova hurt us? In principle, a star exploding close enough to the Earth could be a serious problem, bathing the planet in radiation. But the nearest stars that are massive enough to end this way are comfortably far off, hundreds of light years away at least. And at those distances, a supernova would be a spectacular light in the sky, bright enough perhaps to read by for a few weeks, and nothing more. It would be a wonder, not a threat. So you may set that worry down. The deaths of massive stars are violent beyond imagining. But the violence is local to the star, and we sit at a safe and gentle remove, watching from across an ocean of empty space. Let me give you the human story of how we came to understand this, because it is, again, full of people being doubted and eventually proven right. The word supernova, and the idea that such an explosion would leave behind a tiny, impossibly dense ball of neutrons, came from two astronomers working at Caltech in the 1930s, Walter Baade and Fritz Zwicky. Zwicky was a brilliant, abrasive, difficult man, famous for insulting his colleagues, and many of his ideas were dismissed in his lifetime and vindicated only after his death. In 1934, he and Baade proposed that a supernova was the transition of an ordinary star into what they called a neutron star, an object made almost entirely of neutrons packed together at the density of an atomic nucleus. It was an astonishing leap, made only a couple of years after the neutron itself had even been discovered. Almost nobody took it seriously. It sounded like fantasy. But the logic was sound, and it followed the same thread we have been pulling on all night. Remember the white dwarf, held up by the stubborn refusal of its electrons to be squeezed. A neutron star is the next rung down, when gravity overwhelms even the electrons and crushes them into the protons. You are left with neutrons, and neutrons have their own stubbornness, their own refusal to be packed beyond a certain point. Neutron degeneracy pressure, we call it. So the collapsing core finds a new wall to stand on, made of neutrons instead of electrons. And that is the wall it bounces off. The result is a neutron star. I want you to sit with what a neutron star actually is, because it may be the most extreme object you can still call a star. Take something heavier than the sun, more mass than our entire star, and pack it into a ball about 20 kilometers wide. That is smaller than many cities. The density is so great that a single sugar cube-sized piece of neutron star material would weigh about as much as all of humanity put together. Billions of tons in something you could hold in your palm, if holding it would not instantly destroy you and everything for miles. The surface gravity is so strong that a pebble dropped from a meter up would hit the ground at a fair fraction of the speed of light. These objects spin, often very fast, sometimes hundreds of times per second, left over from the collapse the way an ice skater spins faster as she draws her arms in. And many of them beam out radio waves from their magnetic poles, sweeping across space like a lighthouse. And that lighthouse beam gives us one of the most charming discovery stories in all of science. So let me tell it. In 1967, a young graduate student named Jocelyn Bell, working in Cambridge under the astronomer Anthony Hewish, was studying radio signals from the sky using a field of wires and posts she had helped to build by hand. And in the data, recorded on long rolls of paper by a pen that scratched out the signal, she noticed a strange, regular pulse. A blip, then another, spaced with such perfect precision, about 1 1/3 seconds apart, that it almost seemed artificial. For a little while, they half-jokingly labeled the source LGM-1 for little green men, wondering, not entirely seriously, whether it might be a signal from another civilization. But she found more of them, in different parts of the sky, and a natural explanation made far more sense. What she had found was the lighthouse beam of a spinning neutron star, sweeping past the Earth with metronomic regularity. We call these pulsars, and Jocelyn Bell, now Jocelyn Bell Burnell, had discovered the first one. The Nobel Prize for that discovery went, controversially, to her supervisor, and not to her, one of the more discussed omissions in the history of the prize. She has spoken about it with remarkable grace, and has since given away a very large prize of her own to support students from underrepresented backgrounds. So the next time you hear the phrase pulsar, picture that pen scratching a regular blip onto a roll of paper in a Cambridge winter, and a young woman trusting the strange things she saw. And there is one more kind of neutron star worth meeting, because it pushes the extreme even further. Some neutron stars are born with magnetic fields so powerful that the numbers stop meaning anything. We call them magnetars, and their magnetism can be 1,000 trillion times stronger than the Earth's. A magnetic field that strong would be lethal from a great distance, distorting the very atoms in your body long before you got close. Now and then, the crust of a magnetar cracks, a kind of starquake, and the star releases a sudden flare of energy. In 2004, one such flare reached us from a magnetar roughly 50,000 light-years away, on the far side of our own galaxy. And in a fraction of a second, it released more energy than the sun puts out in many tens of thousands of years. Even from that enormous distance, it briefly disturbed the upper edge of the Earth's atmosphere. These are the most strongly magnetic objects we know of anywhere in the universe, and they are simply the leftover hearts of dead massive stars, spinning in the dark. So now we have a third death, and it is no longer gentle. The massive star builds its onion layers, fuses its way up to an iron core, collapses in less than a second, bounces and blows itself apart in a supernova, leaving behind a spinning city-sized ball of neutrons. The star scatters most of itself across space, and in doing so it scatters something precious, which we will come back to before the night is over. Before we climb to the heaviest death of all, I want to spend a little while on the supernovae that human beings have actually seen, because these are not just theory. People across history, in many lands, have looked up and watched a star explode, without any idea what they were really witnessing. And their careful records still reach us across the centuries. It is one of the quietest pleasures of this subject to know that a stranger 1,000 years ago wrote down the very same light we now understand. The brightest such event in all of recorded history appeared in the year 1006. A new star flared into the sky, so brilliant that observers said it cast shadows and could be read by at night. It was noted in China, in Japan, in Europe, and in the Islamic world, where an Egyptian physician and astronomer named Ali ibn Ridwan described it in careful detail, recording its color and its brightness as it slowly faded over months. None of them knew they were watching a star tear itself apart. They only knew that the changeless heavens had, impossibly, changed. Then, in the year 1054, another guest star appeared, this time recorded most fully by astronomers in China, who noted that it was bright enough to be seen in broad daylight for more than 3 weeks, and remained visible at night for the better part of 2 years before fading from view. For centuries, that was all anyone had, a few lines in an old chronicle about a temporary star. But when modern astronomers pointed their telescopes at the exact patch of sky those records described, they found something extraordinary still sitting there. An expanding, glowing cloud of shredded gas, the scattered wreckage of the very star that had flared so long ago. We call it the Crab Nebula. And at its center, spinning 30 times a second, is a neutron star, a pulsar, the crushed and surviving heart of the star, whose death those watchers recorded in the year 1054. It is one of the only times in history where we can point to a death humans actually witnessed and also see, with our own instruments, the strange small corpse it left behind. 5 centuries later came 2 more, and these were watched by men whose names you may know. In 1572, a brilliant new star appeared in the constellation we call Cassiopeia, and it was studied with great care by the Danish astronomer Tycho Brahe. He wrote a small book about it, and from the Latin word for new, nova, we still take our word for these flaring stars. What unsettled the thinkers of his age was that this new star showed no sign of being close, no sign of being some passing thing in the air. It was out among the fixed stars, in the realm that was supposed to be eternal and unchanging, and yet there it was, plainly new. It helped crack open the old belief in perfect, changeless heavens. Then, in 1604, yet another new star blazed up, and this one was studied by Johannes Kepler, the great astronomer of planetary motion. It is the most recent supernova seen with the naked eye within our own galaxy. Since Kepler's star faded more than 400 years ago, no one has seen another one explode in the Milky Way with their unaided eyes. We are, in a sense, overdue. But the nearest one in modern times came in 1987, and it gave us a gift that confirmed everything we had worked out about how massive stars die. In February of that year, a star exploded in a small companion galaxy near our own, called the Large Magellanic Cloud, close enough that it could be seen without a telescope from the southern hemisphere. It was the nearest supernova observed in nearly 400 years. And here is the beautiful part. A few hours before the light of the explosion reached the Earth, detectors deep underground, in Japan, in the United States, and in what was then the Soviet Union, caught a tiny burst of those ghostly particles, the neutrinos, roughly 24 of them in all. Remember that when the iron core collapses, it floods out neutrinos, and remember too that light has to fight its way out through the whole body of the star, staggering and bouncing, while neutrinos pass straight through almost everything as if it were not there. So the neutrinos left the dying star first and arrived first, hours ahead of the light, exactly as the theory said they should. A handful of ghost particles, caught in tanks of water buried under mountains, confirmed that deep inside a star 200,000 light-years away, a core had collapsed in less than a second and made a neutron star. We had predicted that on paper, and the universe sent us the receipt. But there is a heavier death still, and to reach it we have to ask one more question. We saw that a white dwarf has a maximum mass, the Chandrasekhar limit, above which the electrons give way. Does a neutron star have a limit too? Is there a mass so great that even the stubbornness of packed neutrons cannot hold the line? There is. And when a collapsing core crosses it, nothing in the known universe can stop the fall. The men who first worked this out are familiar from another, heavier part of history. Robert Oppenheimer, who would later lead the project that built the first atomic bomb, turned his attention in the late 1930s to the question of how massive a neutron star could be. In 1939, with his student George Volkoff, building on earlier work by the physicist Richard Tolman, he calculated that neutron stars, too, have a maximum mass. Push a core above that limit, which we now think lies somewhere around 2 to 3 times the mass of the Sun, and the neutrons cannot hold. We call it the Tolman-Oppenheimer-Volkoff limit. And in that same remarkable year, 1939, Oppenheimer published another paper, this time with the student Hartland Snyder, working out what happens to a core that exceeds every possible limit. Their answer was that it simply keeps falling. Nothing stops it. The matter collapses inward without end, and around it, space itself closes over like water over a stone. That is a black hole, the most extreme death a star can suffer. Let me try to make a black hole feel a little more imaginable, because the word gets used so loosely that it has almost stopped meaning anything. Here is the heart of it. Gravity bends the paths that things take through space, including light. Near an ordinary object, the bending is gentle. But if you crush enough mass into a small enough space, the bending becomes total. There comes a distance from the center, a sphere we call the event horizon, where the pull is so strong that not even light, the fastest thing there is, can travel outward fast enough to escape. Anything that crosses that boundary, any light, any matter, any signal, can never come back out. It is not that escape is hard, it is that there is no longer any direction that leads out. All paths lead inward. The size of that boundary was worked out astonishingly early, in 1916, by a German physicist named Karl Schwarzschild, who solved the equations while serving as a soldier on the Russian front during the First World War, and who died of an illness contracted in the trenches just months later, at the age of 42. He never knew that the strange radius he had calculated, the Schwarzschild radius, would one day be understood as the edge of a black hole. He solved the mathematics in the mud of a war and did not live to see what it meant. So the most massive stars, when their iron cores collapse and exceed even the neutron star limit, do not bounce. They do not make a neutron star. They fold inward past every wall, past the electrons, past the neutrons, past every kind of stubbornness nature can offer, and they vanish behind an event horizon, leaving a black hole where a brilliant blue star used to be. In some cases, there is still a supernova, as the outer layers are blown off. In other cases, for the very heaviest stars, the whole star may simply collapse inward and wink out, with little or no explosion at all, the light going dark as though someone had quietly closed a door. For a long time, all of this was pure mathematics, ink on paper, and many serious scientists doubted that black holes could really exist. The very phrase black hole only came into common use in the 1960s, popularized by the American physicist John Wheeler, who had a gift for memorable names. Before that, they were spoken of, if at all, as a strange and probably unreal corner of the equations. It took decades to find good evidence that nature actually makes them. The first strong case was a faint, invisible object in the constellation of the Swan, named Cygnus X1, found in the 1960s as a powerful source of X-rays. When astronomers looked, they saw a large bright star that appeared to be orbiting something heavy and unseen, something too massive to be a neutron star and yet giving off no light of its own, while gas torn from the companion spiraled in and heated up and screamed in X-rays before it vanished. It looked in every way like a black hole quietly feeding. It was so striking and yet so hard to prove for certain that two famous physicists, Stephen Hawking and Kip Thorne, made a friendly bet about it in 1974. Hawking, who had done more than almost anyone to understand black holes, bet that Cygnus X1 was not one, as a kind of insurance policy, so that if the black hole he had spent his life studying turned out not to exist, he would at least win the wager. By 1990, the evidence had grown so strong that he conceded and paid up. I want to give you one strange and gentle feature of a black hole before we move on, because it touches on time itself. Suppose you could watch from a safe distance as something fell toward the edge of a black hole, toward that boundary we called the event horizon. You would expect to see it fall in and disappear. But that is not what you would see, because gravity that strong bends not only the paths of light, but the flow of time. You would see the falling object slow down as it approached the edge, slower and slower, its light stretching and reddening and dimming, until it seemed to hang there, frozen at the brink, fading away, but never quite crossing. From your point of view, it would take forever to fall in. And yet, from the point of view of the thing falling, nothing strange would happen at all. It would simply fall straight through the edge and continue inward in moments, never noticing the boundary at all. Two completely different stories of the same event, both true depending only on where you stand. There is something dreamlike in that, and I will let it stay soft and not press it. And in our own time, we have finally seen one. For a century, the dark circle at the heart of a black hole was something only the mathematics could describe. Then, in 2019, a team of astronomers working together across the whole planet, linking telescopes from Hawaii to Spain to the South Pole into a single instrument the size of the Earth itself, produced the first true image of a black hole. It was the enormous one at the center of a distant galaxy called ADM 87, 55 million light-years away. And the picture showed exactly what Schwarzschild's mathematics had predicted in a trench more than 100 years earlier. A dark, round shadow, ringed by a glowing halo of hot gas, the silhouette of a hole in space. A few years later, the same team turned their attention closer to home and imaged the black hole at the center of our own galaxy, the one we live inside. A giant 4 million times the mass of the Sun, sitting quietly in the constellation of the Archer. We had finally looked the thing in the face. And that gives us our fourth death. The heaviest. The black hole. The point past which the falling never stops. Now, I told you at the start that we would walk through every way a star can die. And we have one strange path left. A death so unusual that it leaves nothing behind at all. Not a white dwarf. Not a neutron star. Not even a black hole, just an expanding cloud and an empty space where an enormous star used to be. This is the rarest and the eeriest death of all. And it happens only to the most colossal stars, the giants among giants. Let us go there slowly, because the physics behind it is genuinely beautiful and a little counterintuitive. Imagine a star not 10 or 20 times the mass of the Sun, but 150, 200, 250 times the mass of the Sun. Such stars are extraordinarily rare, and they were probably more common in the early universe than they are today. But they can exist. They are blindingly bright, blue-white furnaces, and they live only a few million years. The core of such a star, late in its life, reaches a temperature so staggeringly high that something new becomes possible, something that has not entered our story yet. At those temperatures, the core is filled not just with matter, but with intensely energetic light, gamma rays so powerful that they carry more energy than the matter around them. And here is the strange thing that very energetic light can do. Under the right conditions, a pair of gamma rays can collide and turn into a pair of particles, an electron and its mirror image, a positron. Light becomes matter. Energy congeals into a particle and its antiparticle. This is real. It has been demonstrated in laboratories, and in the core of one of these colossal stars, it begins to happen in earnest. Now, why does that matter for the star's life? Think back to the balance we have leaned on all night. A star holds itself up because the energetic radiation in its core pushes outward against gravity. The light is part of what holds the walls open. But if that light starts turning itself into particles, then the pressure it was providing suddenly drops. The very radiation that was holding the core up is converting into matter and stepping out of the fight. The support sags, and so the core, robbed of some of its outward push, begins to contract. And here is the trap that gives this death its name. As the core contracts, it heats up. And as it heats up, even more of the light turns into particle pairs, which removes even more pressure, which makes the core contract still further, which heats it still more. It is a runaway. The star has fallen into a feedback loop that feeds on itself, and the technical name for it tells you exactly what is happening. We call it the pair instability, because the production of particle pairs makes the star unstable in a way it cannot recover from. The contracting, overheating core now races toward the temperatures at which its oxygen and silicons can fuse explosively, all at once. Not in a controlled way, but as a single, enormous thermonuclear detonation through the heart of the star. And for the most massive of these stars, that detonation releases so much energy, far more than an ordinary supernova, that it does something nothing else in our story does. It blows the entire star apart. Completely. There is no core left to collapse, no remnant, no white dwarf, no neutron star, no black hole. The whole vast star is unbound and scattered into space, every last bit of it, in one of the brightest explosions the universe can produce. We call it a pair instability supernova. And afterward, where a star 200 times the mass of the Sun once blazed, there is only an expanding shell of debris and a strange, clean emptiness. I find that an oddly haunting thought, and I want to let it sit with you for a moment in the quiet. The smallest stars, the red dwarfs, are too gentle to do anything but fade. The middling stars leave a white dwarf. The heavy stars leave a neutron star. The heaviest leave a black hole. But somewhere in between, among the true titans, there is a narrow band of stars so enormous that they erase themselves entirely, leaving nothing of their bodies behind, only the memory of light and an outward rushing cloud. They are the only stars that truly die without a trace. And we have, in recent years, found a handful of distant explosions that look very much like this rare death actually happening, confirming that the universe does, occasionally, undo its largest stars in this strange and total way. Above even those, by the way, for the very most extreme objects, the ones beyond about 250 times the mass of the Sun, the physics flips once more, and instead of detonating, they collapse directly into enormous black holes, the gamma rays growing so fierce that they break apart the very nuclei the star spent its life building, and the whole thing falls inward. But the pair instability supernova, the star that leaves nothing, is the strangest and rarest death we know, and it makes a fitting end to our catalog of how stars die. So let us gather what we have, gently, before we turn toward the wider meaning of all this. We have 5 deaths, sorted, as I promised at the very start, by the single fact of mass. The smallest stars, the red dwarfs, less than half the mass of the Sun, simply fade. Over trillions of years they burn nearly all their fuel, then contract and cool into small dark embers, the gentlest goodbye there is. A death no star has yet had time to complete. Stars like the Sun, from roughly half the mass of the Sun up to about 8 times it, swell into red giants, fuse helium into carbon and oxygen, and then breathe their outer layers away into a glowing planetary nebula, leaving behind a white dwarf, an Earth-sized ball held up forever by the refusal of its electrons to be squeezed any tighter. Heavier stars, from about 8 times the Sun's mass upward, fuse their way up the ladder to an iron core, collapse in less than a second, and explode as a supernova, leaving behind a city-sized neutron star denser than an atomic nucleus, sometimes sweeping the sky with a lighthouse beam. The most massive stars collapse past even the neutron stage, folding inward behind an event horizon and leaving a black hole, a place where gravity has won so completely that not even light can climb back out. And the rare titans, in a narrow band of enormous mass, fall into the pair instability and detonate so violently that they scatter every last piece of themselves into space, leaving no remnant at all. That is, as the title promised, more or less everything about how stars die. But I would be leaving the story unfinished if I stopped there, because the death of a star is not the end of anything. It is, in the truest sense I know, a beginning. And this is the part I most want you to carry with you into sleep. Let us go back to those supernovae, the explosions of massive stars. We said the star fuses its way up to iron and can go no further by ordinary means because iron will not release energy when it fuses. But the universe is full of elements heavier than iron: gold, silver, lead, uranium, the copper in the wires of the lamp beside you, the zinc in your body, the iodine your thyroid needs, the silver in an old photograph. Where did those come from, if stars cannot make them by ordinary fusion? The answer is the explosion itself, and the collisions that follow it. In the unimaginable violence of a supernova, and even more so in the catastrophic collisions of neutron stars with one another, conditions become so extreme, with so many free neutrons flying about, that atoms can capture neutron after neutron in rapid succession and build up into the heaviest elements there are. The gold in a wedding ring was very likely forged in such an event, billions of years ago, in the death throes of a massive star or the collision of 2 stellar corpses, long before the Earth existed. And we have, astonishingly, watched this happen. In 2017, instruments on the Earth felt the faint tremor of 2 neutron stars, 2 of those city-sized corpses, spiraling together and colliding in a galaxy some 130 million light-years away. We felt the collision first as a ripple in the fabric of space itself, a gravitational wave. the kind first predicted by Einstein a century before, and first directly caught only in 2015. And then telescopes around the world swung to the spot and watched the glow of the aftermath. And in that glow, astronomers saw the fingerprints of freshly made heavy elements, including gold and platinum, being forged in real time in the wreckage of the smash. Whole worlds worth of gold, made in a few seconds by two dead stars falling into each other. So when you next see something gold, a ring, a chain, a coin, you can hold the quiet knowledge that the atoms in it were almost certainly born in a catastrophe like that one, in the violent meeting of two stellar corpses, unimaginably long ago and unimaginably far away, and then carried here to become an ordinary thing you can hold in your hand. And then it was scattered across space, mixed into a vast cloud of gas and dust. And that cloud, ages later, collapsed under its own gravity to form a new generation of stars and planets, including our sun and our earth and everything on it. Here is the thought I want to leave with you, and I want to say it plainly, without dressing it up, because it does not need dressing up. The calcium in your bones, the iron in your blood that makes it red, the oxygen filling your lungs as you breathe slowly now, the carbon that forms the backbone of every living thing, all of it was made inside stars, and most of it was scattered into space by the death of stars. You are, quite literally, made of the ash of dead stars. The atoms that make up your body were forged in stellar cores and flung outward by stellar deaths billions of years before there was an Earth for them to land on. When a star dies, it seeds the universe with the very stuff that life is built from. There has never been a more generous death. The men and women who pieced this together deserve to be named, because it took the whole of the 20th century and a great deal of patient argument. We have met Cecilia Payne, who learned what stars are made of, Hans Bethe, who learned how they burn, Chandra Sekhar, who learned the limit that dooms them, Zwicky and Body, who imagined the neutron star, Oppenheimer, Volkoff, and Snyder, who pushed the logic all the way to the black hole, Schwarzschild, who solved the mathematics in a trench, Jocelyn Bell Burnell, who heard the lighthouse pulse. And the question of where the heavy elements came from was answered most fully in a famous paper in 1957 by Margaret and Jeffrey Burbidge, William Fowler, and Fred Hoyle. 4 scientists who showed, element by element, how the stars cook up the periodic table and then, in dying, hand it on. Fred Hoyle, who had a gift for vivid phrasing, is the one most often remembered for the simple, staggering summary of it all. That we are, each of us, made of the material of the stars. He meant it not as poetry, but as plain physical fact, and it is. Now let us widen out one last time, and then we will let the story come to rest. When you look up at the night sky, you are not really seeing the present at all. You are seeing the past, layered and mixed together. The light from a nearby star may have left it a few years ago. The light from a star across the galaxy may have left it tens of thousands of years ago, before the first cities were built. And some of the faint smudges you might glimpse are entire galaxies whose light set out millions of years ago. This means something quietly astonishing. Some of the stars you can see in the sky tonight are, at this very moment, already dead. They have already gone through everything we have described, the swelling, the exhaling, the collapse, the explosion. But the news of it has not reached us yet, because that news travels at the speed of light, and the universe is wide. You may be looking at a star that no longer exists, lit only by a message it sent out long ago, still on its way to your eyes. The sky is full of beautiful ghosts. And there is one star in particular I want to leave you to think about, because you can very likely see it yourself on a clear night, and it is already living on borrowed time. In the constellation of Orion, the Hunter, one of the easiest shapes to find in the winter sky, there is a bright star marking one of his shoulders, with a warm, slightly reddish color. Its name is Betelgeuse. It is a red supergiant, an enormous, swollen star far heavier than the Sun and so vast that if you placed it where the Sun is, its surface would swallow the orbits of the inner planets entirely. And Betelgeuse is near the end. It has burned through most of its life and is in the late, unstable stages we have been describing, somewhere on the road toward an iron core. Sometime in the astronomical near future, which could mean tomorrow night or could mean 100,000 years from now, Betelgeuse will collapse and explode as a supernova. In late 2019 and early 2020, Betelgeuse did something that briefly made astronomers and the public wonder whether the moment had come. It dimmed, dramatically, fading to a fraction of its usual brightness over a few months. For a little while, there was real excitement that we might be about to watch one of the great stars of our sky die. As it turned out, the dimming was caused by a vast cloud of dust the star had coughed out, drifting across our view like a veil. And Betelgeuse soon brightened again. It was not the end after all. But the end is coming, and when it does, Betelgeuse, at its safe distance of several hundred light years, will flare into a light bright enough to see in broad daylight, possibly rivaling the half-moon, and it will hang there in the sky for weeks before slowly fading. Whoever is alive to see it, human or otherwise, will witness exactly the death we have walked through tonight, the collapse and the bounce and the explosion, playing out on a star they had known their whole lives as a quiet point in Orion's shoulder. It is, in a way, a death already scheduled, waiting only for its light to reach us. And our own star, the Sun, sits comfortably in the middle of this whole story, in no danger at all for a very long time. It is about 4.5 billion years old, roughly halfway through its quiet, hydrogen-burning life. In about 5 billion years, it will swell into a red giant, swallow the inner planets, exhale a planetary nebula, and settle into a white dwarf, glowing ever fainter, cooling over tens of billions of years toward a final dark. That is the future. But it is so distant, so impossibly far beyond any human concern, that it should bring you no anxiety at all, lying here tonight. The sun that warmed your skin today will keep warming the earth for longer than complex life has so far existed. Its death is not your concern. Its long, steady life is your inheritance. Think about the whole arc of it once more, softly as your thoughts begin to loosen. A cloud of gas, mostly hydrogen left over from the birth of the universe and salted with the ash of older stars, drifts in the dark. Gravity gathers it. It collapses, heats, ignites, and a star is born. For millions or billions or trillions of years, it holds the long balance, fusion pushing out, gravity pulling in, shining steadily into the night. And then, when the fuel runs low, the balance tips, and the star ends in the way its mass decreed at birth. It fades, or it exhales, or it explodes, or it collapses, or it scatters itself entirely. And in nearly every case, it gives something back, returning its substance to the dark from which the next stars and the next worlds and the next living things will be made. The death of stars is how the universe makes everything that matters. It is how it made you. There is a kind of peace in that, I think. The kind that is easy to feel late at night when the day has finally let go of you. Everything that ends in this story also begins something. Nothing is truly lost. The light goes out in one place and arrives, transformed in another. The atoms that were a star become a planet, become an ocean, become a person lying quietly in a dark room, listening to a voice describe the deaths of stars made of those very stars, slowly drifting towards sleep. And perhaps that is the gentlest way to hold the whole subject, now that we have walked through all of it. We began the night with a worry hidden inside the word death, and we can end it having seen that the word means something different for a star than it does in our ordinary fears. A star does not vanish when it dies. It changes its address. It hands its substance on. The red dwarf becomes a quiet ember that will outlast the galaxies. The sun-like star becomes a glowing nebula and a small, bright heart that cools for ages. The massive star becomes a city of neutrons or a black silence in the fabric of space, and either way, it flings the elements of life across the dark. Even the rare titans that erase themselves leave the universe richer for their passing. There is not a single death in all of this that ends in nothing. Not really. Each one is a giving, a passing of light and matter from one form into the next, in a chain that reaches all the way down to the warmth in your own body tonight. You do not have to do anything with that thought. You can simply let it be true while you rest. So let me leave you there, gently. Where you are, notice, if you still can, the simple weight of your body against whatever is holding it up. The bed, the chair, the floor, all of it ultimately resting on the same gravity that crushes stars and the same matter that the stars made. Notice your breathing, slow and even, the oxygen moving in and out. Oxygen forged in some long-dead star and scattered here for you to use tonight. There is nothing left to understand, nothing to hold on to, nothing to finish. The stars have been dying for 13 billion years without your help, and they will go on dying for trillions more, patiently, in their own time, whether or not anyone is awake to watch. You can let go now. The light will keep traveling. The sun will rise again on schedule. And somewhere far overhead, in the deep quiet, a small red star that will outlast everything is burning so gently that it has barely begun to die and will not finish for 10 trillion years. Let that thought be the last one. A small, patient light in the dark, in no hurry at all, the way you no longer need to be. Rest now. The stars will keep watch.